good afternoon, everybody. We're going to continue our exploration of linear programming. Now, of course, you know, our long-term goal in linear programming is to develop a polynomial time algorithm to find the optimum. But we decided that that's too hard to tackle all at once. So we can lower our objective to just some kind of algorithm to find the optimum, right? Maybe we give up on polynomial time for starters, right? But even that is not really clear how to do. And so we back off a little farther and say maybe we can find an algorithm to just verify that our optimum is the optimum if somebody gives us the optimum. But even that, it's not clear we can do because we're not sure yet whether it's possible to write down the optimum in polynomial space, in finite space, much less polynomial space, right? Maybe the optimum is irrational, and so we can't even record it. Okay? So even that seems so daunting that we sort of backed off further. So let's forget about the inequalities and let's just talk about linear systems. And so with linear systems are easier, and we were able to start making some progress on these things. And so we did show that indeed the solution to a linear system has polynomial size. Right? We can write it down with a polynomial number of bits, where that polynomial is in the number of bits in the input numbers and also in the sort of structural size of the problem, the number of variables n and the number of constraints m, right? In m, which is the number of constraints, and n, which is the number of variables, and in the input number sizes. Right, so it is indeed possible to write down the solution of a linear system, right? It's also, of course, easy to check that you have a solution to a linear system. If somebody gives you one, you plug it in, and that tells you whether it is indeed the correct answer to the linear system in polynomial time, right? Now, last time we showed something less obvious, right? Which is that it's also possible, we developed this duality theory for linear systems, which said that there's a way to provide a proof that there is no solution to a linear system, right? We demonstrated that you can show that there is no solution by showing that a different linear system has a solution, right? So given your input linear system A, we showed how to construct a different linear system B such that there is a solution to A if and only if there is no solution to B, right? And so somebody can show you that there is no solution to A by giving you a solution to B, and that solution to B is one that you can check in polynomial time. So this really resolved things for linear systems, that we can check a solution in polynomial time, and we can also verify the lack of a solution in polynomial time. And we also mentioned, although we didn't go into details, that, of course, Gaussian elimination, which we're all familiar with, is a method that can be used to actually construct the solution in polynomial time. All right? And now we're trying to carry all of those ideas back out from linear systems to linear programming, to problems that involve linear inequalities as well as equalities. And so we started last time to investigate the structure of the optimum solution. And I defined for you, we drew some pictures, right? And we made an argument that intuitively, you're not going to find the optimum to a linear program in the middle of the polytope. Rather, you can focus your attention on the corners of the polytope as places where the optimum is going to be, right? And so we defined, maybe I should look at my notes. We gave a definition of what these corners are, right? And we actually I gave you 3 descriptions. The one we spent the most time on was what was called a basic feasible solution, right? Which is just a feasible solution that is also basic. So what's important is to talk about a basic solution. A basic solution is a point that is the intersection or sorry, let me use the language I used last time, that is tight for n linearly independent constraints. And also, for technical reasons, tight for all the equality constraints. So remember, you're tight for a constraint if the value of your point, if you meet the boundary of that constraint, right? You're on the bounding hyperplane that defines that constraint. And if you're feasible, you're certainly going to be tight for all of the equality constraints. You're going to satisfy them, which means that you're on the hyperplane that one of those equality constraints defines. There are plenty of feasible points that are not tight for any of the inequality constraints, right? So here we have a point that is not tight for any of the inequalities that define this polytope, right? Now here we have a point that is tight for one of the inequalities and loose for all of the other ones. Here we have a point that is tight for 2 of the inequalities, and visually you can see that they're linearly independent. So this point is a basic solution, and because it's a feasible point, it's a basic feasible solution, right? This is a feasible point that is not a basic solution. Okay. And last time we showed that any standard form LP with an optimum has one at a basic feasible solution, right? We showed this via a rounding procedure. That takes any optimum point and moves it to a basic feasible solution, right? We said if you're not a basic feasible solution, then there's some slack, right? There's some directions you can move without violating feasibility, and so you move in one of those directions until another constraint becomes tight, right? And now you've got a slightly more basic solution, and you just keep on moving to make things tighter, to make more and more constraints tight until you have n-tight constraints. And that's what we finished with last time, was this argument that you can always do this in standard form, right? I showed you that in non-standard form, you can have some weird pathological exceptions, right? I gave you a canonical form linear program where the only constraint was this horizontal line, and now every point on the line, if your objective function is pointing up, and your constraint is pointing straight down, then every point on this line is an optimum point. But there are no basic feasible solutions here because there's only one constraint. So there's no place where there's an intersection of two to make a basic feasible solution. Okay? Now, there's a slight mystery here, right? Because I showed you 2 lectures ago that every linear program can be transformed into standard form, right? And once it's in standard form, we know that there is a basic feasible solution. So how is it that I can have a linear program where there is no basic feasible solution optimum, and by doing a bunch of simple transformations that we saw last time, somehow a basic feasible solution optimum appears out of thin air, right? How does that basic feasible solution optimum appear? And I'm not going to answer that here. I think it's a good little exercise for you to think about that, go back to look at the transformation that makes a linear program into a standard form linear program and say, how is it creating basic feasible solutions when there weren't any previously? Okay, that'll give you some more insight into these transformations. All right. Now, last time I also gave 2 other definitions of corners. One of them was what's called a vertex, okay, which is a feasible point that is not a convex combination of 2 other feasible points. Okay. Or put into plain language, a point that is not on a feasible line segment. Okay. So again, this point here, I can draw a line through it that connects 2 other feasible points, right? And so this point that I started with is a convex combination of these 2 points, which means that it is not a vertex. Okay? And the last definition I gave was what's called an extreme point. An extreme point is a point that is the unique optimum for some objective function, some direction. Right? It is the only point that is the farthest in some direction in this polytope, right? So again, you can look at this and see, well, obviously there's no direction in which this is the farthest point, right? There's also no direction for which this is the unique farthest point, right? There is a direction in which this point is optimal, but in this direction there are many other optimal points, right? This vertex on the other hand, or basically this corner on the other hand, this does have a direction in which it is the unique optimum. Okay. And it's not a coincidence that I was able to go back and look at these pictures, because in fact these 3 definitions, basic feasible solution, vertex, and extreme point, they all define the same thing. Okay? And so I'm going to sketch that for you. Where did I write my notes? I'm going to give you a sketch of how you argue that these 3 things are the same. So first I'm going to show you that, or sketch, that every extreme point is a vertex. Okay. And the way that I'm going to do that is the contrapositive. I'm going to show that everything that is not a vertex is also not an extreme point. Okay. So what does it mean for a point not to be a vertex? What does that mean according to our definition? Yeah?
There's a feasible line segment.
Good.
That is on.
So there's a feasible line segment through x. Now, how do we use the existence of that feasible line segment to argue that x is also not an extreme point? Well, by contradiction, right? So we're suppose that we're extreme in direction d, right? In other words, that dx is a unique optimum. I want to show that that's not possible. Yeah? You're going to have to join the class in order to answer a question.
Unfortunately.
No, go ahead.
Like, so I'm guessing, but go like in one direction, it's like it either decreases value or increases value, and if it like increases value, then you're done. But if it like decreases value, then you go in the opposite direction.
Good. That's absolutely right. Clearly, you should join the class. So if I consider x, and I've got this line, you're making an argument that I can try moving on this line, right? And one possibility is that if I move on this line, it improves the value of the objective. I'm using careful language to avoid talking about min or max, right? But moving in one direction, you might find that it improves the value of the objective. Now, if moving in one direction improves the value of the objective, what does that tell you?
It's not unique.
Well, it actually tells you more than that. If moving takes you to a better objective value, what does that mean about x?
It's not an optimum.
It's not optimum, right? So try moving on the line. Okay. If it improves, that tells you that x is not optimum. Right? Now, another possibility is that it might get worse in the direction you move. What does that tell you? Or what should you do in that case? Yeah? Yeah, if it gets worse in one direction, then moving in the opposite direction improves things, and you're back in the first case. And so again, you have the fact you have that x is not optimum. Does this exhaust all the possibilities?
It could just not change.
Right. The last possibility is that it doesn't change. Now, if moving on this line doesn't change the value of your objective, what does that tell you? Yeah?
It's not unique.
Not unique. Okay, so this line, this feasible line makes it impossible for you to be the unique optimum in any direction. So that means you're not a extreme point. Okay, good. So extreme point implies vertex. Now I also claim that vertex, yeah, well, let's start another board. Also going to tell you that vertex implies BFS. Okay. If there's no convex combination, then you're at a basic feasible solution. And again, I'm going to do this by contrapositive. I'm going to suppose I am not at a BFS, and I am going to conclude that I am not at a vertex. Okay? So let's suppose x is not a BFS. What does that mean from the definitions? Yes?
It can make it better.
Not necessarily. Not necessarily. You could be at a, I mean, right? If this is the objective, and I'm here, I'm not at a BFS, but I can't make it better. Yes?
Fewer than 2 linear.
Right. The definition says that there are fewer than n tight constraint, and linearly independent, but don't worry about that, constraints. Right? If you have a linearly dependent constraint, then your value on that constraint is determined by your value on the other constraints. And so you don't even really need to think about that dependent constraint. Okay? So if there are fewer than n tight constraints here, what can I do? Yes?
You have some degree of freedom.
Right. There exists a degree of freedom. And since we're talking about linear systems here, that degree of freedom includes at least a line, right? Another way to say this is that the intersection of the tight constraints is a subspace of dimension at least 1, and so it contains a line. Right? Now, what do I know about this line? Suppose that I move a little bit on this line. What can I say? Yeah?
It's still feasible.
Right. A slight move on this line is still feasible. Right? Because in order to become infeasible, you have to cross a constraint. And you're not moving against any of the tight constraints, so the only way to become infeasible is to cross one of the loose constraints. But in order to cross a loose constraint, you have to reach it, and that takes you a finite distance. So there's some infinitesimal distance you can move and still be feasible, right? And that means, that, and you can do this in both directions, right? On this line, you can do this in both directions. And so if you do this in both directions, this gives you 2 points whose convex combination is x, right? You just move the same distance in each direction away from x, and now their average is x itself. And so that tells you that you're not at a vertex. Okay? So the last implication that we need to look at is that if you're at a BFS, then you're at an extreme point, right? And then we'll have this chain of equivalences that shows that they're all within. Okay. So in order to keep the notation simple, I'm going to just look at standard form, at a standard form linear program. It's true for any linear program, but it's just notationally a little bit less messy if we talk about standard form. Okay. So what we're going to do is let T be the set of tight constraints, of tight inequalities. Okay. Remember that in standard form, right? Here you have your goal is to minimize Cx such that Ax equals b. These are all equality constraints and are always going to be tight. And your inequalities are all of the form x greater than or equal to 0, right? So in standard form, what does it mean for a constraint to be tight? In other words, these are the variables xi, which are equal to 0. Yes? The other variables, the other xi, which are not tight, that means they're positive. Okay? So I'm just going to use this to define an objective function. I'm going to define C to be equal to, let me say it this way, Cx to be just equal to the sum from I equals, or the sum over I in T of xi. Okay. In other words, my vector C just has a 1 for all of the tight x's and a 0 for all of the other ones. Okay? And I claim that the point x is extreme for this objective function. So that means I have to show you that it's the unique optimum under this objective function, right? So is it optimal? Well, what is the value of Cx if C is this objective function? Yes. 0. It's 0, right? Because it only sums the x's that are tight, right? And those x's, they're tight. They all have value 0, right? So that tells me that Cx equals 0, right? And I just need to argue that that is optimal and that there aren't any other optima, right? Now, is this optimal? How do I know that this is optimal? Yeah?
They're all positive.
Well, they're all non-negative, right? The constraints, the standard form says all of your variables have to be non-negative, right? If all your variables are non-negative, and I have a bunch of just ones in my objective function, then I can't get a negative value, right? So whatever the value of the objective is, it's always non-negative, okay? And so 0 is the best possible, so this is indeed an optimum point. Okay. Let's consider any other point, which is not x, okay? But that is feasible, okay? So if x prime is a different point, okay, that means that it has to have, that means it has to be loose for some one of these, for some one of these xi and t. Right? If x prime was tight for every one of these constraints, well, there are n linearly dependent constraints. It would have to be the same point, right? The only point that can be tight for all of these constraints is x. So any other point has to be loose for at least one of them. What does it mean if it's loose for a different, for one of the constraints in T? Yeah?
Cx has to be greater than 0.
Exactly, right? If it's loose for some constraint, that means that x prime sub I is greater than 0, right? But if x prime I is greater than 0, it means that Cx prime is greater than 0. Because again, there's no way to subtract something off to cancel out that positive contribution, because all of the coefficients of C are non-negative. Okay? So that proves what we want. That proves that indeed x is the only optimum for this particular objective function, right? More generally, what we're doing is we're taking, right, if we want to make this, if we want to show that this point is an extreme point, we just look at the tight constraints. Each of these tight constraints has some normal, right? Some perpendicular vector, and if we just add up those normal vectors, we get an objective for which this is the unique optimum. Okay, because essentially, as soon as you become loose on any one of these constraints, it changes the contribution that normal gives to the objective function and makes it worse. Okay. All right, so that completes the proof that these three things are all the same: basic feasible solution, vertex, extreme point. So now I can use any one of the three terms, and they're all interchangeable, right? So I'll often say vertex because that's the shortest. Sometimes I'll say basic feasible solution because that's the most important aspect, is this intersection of n tight constraints. Okay? But what use is this? What use is it to know that the optimum can always be found at a vertex? Well, it actually immediately gives us something that wasn't clear until now. Okay? It gives us an algorithm for linear programming. Okay? So this is linear programming algorithm 1. Given what we know, that the optimum is at a basic feasible solution, What is an algorithm for finding the optimum? Yes?
Let's check all of them.
Right. Try every basic feasible solution. Okay. Now, what does try mean? Well, you need to compute the x at that BFS, and then compute its objective value, Cx, right? And you just you find all of those x's, you compute all of the objectives, and you keep the one that's the best, largest, smallest, depending, right? And, or sorry, is this doable? Can you find the x that is at a basic feasible solution? Remember, basic feasible solution is defined by the fact that there are these n tight constraints. Yes?
You set like the n inequality equal to 0, and then you have a linear system.
Exactly. What you do is you define the specification that these n constraints are tight, specifies a system of n linear equalities. Right? And if they're linearly independent, then it's a solvable system of linear equalities. Right? Because the determinant of that matrix is non-zero. That's the criterion that we looked at for solvability of linear systems. Okay. So we can solve it, right? And we know two important things, right? We know that we can solve it and write it down. We can solve in polynomial time, and we can write down the solution in polynomial space. Okay? Because it's a linear system. Okay? Now, once we've done that, we should check feasibility, right? How do you check feasibility of the point x that you've computed? Well, you just test it against all of the other constraints, right? And if it is feasible, you compute the objective value, and again, you keep track of the best objective you find among the feasible, among the basic feasible solutions that you find this way. Okay. And again, this sort of shows us, just in passing, that the solution to any linear program, not just a linear system, but to an LP, is something that you can write down in polynomial space, right? Because it is the solution to a linear system. How long does this take? Right? If we have m constraints and n variables, then how long does it take us to check all the basic feasible solutions? Yeah?
M choose n.
Exactly. M choose n candidates. Must be checked. In other words, the runtime is roughly m to the nth power. Okay, this is already something, actually. This means that we can solve a linear program over a constant number of variables in polynomial time. Right? And this, again, this is not crazy. This happens all the time, right? You have 3 variables of interest but you have 300 constraints that must all be met by these variables. Right? And what this is telling you is that you can solve that linear program just by brute force enumeration of which set of 3 constraints is tight at the optimum. Okay. All right, so that's kind of a milestone, right? We have a finite algorithm for linear programming, and it's polynomial time in constant dimension. And it also tells us that regardless of the dimension, at least you can write down the answer, the optimum solution to any linear program in arbitrary dimension. It only takes polynomial space. So already we've made a lot of useful progress that required non-obvious insights. Okay? But now we're going to try to improve things. We're going to try to acquire to manage some actual polynomial time algorithms. But this is still going to involve a pretty big detour. Because we're not going to go straight for algorithms for finding the solutions. We're just going to start talking again about checking optimality, or verifying optimality. Okay, so somebody gives me a claimed optimum for the linear program. Can they give me a efficiently checkable proof that it is the optimum? Okay. I mean, obviously, I could check all of the vertices, and in doing so, compute the optimum myself and check if their answer is correct. But that's incredibly inefficient. You know, maybe even if it's hard to compute the optimum, maybe it's easy to just check whether a particular proposed solution is the optimum. Right? We can even back off a little bit and ask about verifying feasibility. So if I give you a collection of linear inequalities, it's very easy to prove that there's a feasible solution. You just show me one, right? Here is a point that satisfies all of the inequalities. But how might you prove that there is no point that satisfies all of the inequalities, right? We saw how to do that. We saw this interesting trick with linear systems where we gave a different linear system that we used to prove that there was no solution to the first linear system. Is there some kind of similar trick that we can play here, right? Somewhere in the middle, there's the question of verifying some bound on the opt. That the optimum is less than some bound k, or if it's a maximization problem, or if it's a minimization problem, verifying that the optimum is lower bounded by some quantity k. Okay? And that's what we're going to spend the rest of today's lecture on, is thinking about how to demonstrate bounds on a linear program in an easily checkable way. Okay? And this is going to take us to LP duality, which is one of the deepest and most powerful ideas that has come out of algorithms. We're going to be studying it in the context of linear programming, but it turns out to drive a lot of other algorithms that do not look like linear programming on the surface, but it turns out that there is a linear program hiding inside of them. And so duality makes a big difference. Okay? And in particular, LP duality gives us for free the max-flow min-cut theorem, the feasible prices that we use to optimize min-cost flow, the existence of Nash equilibria in zero-sum two-player games, and lots of other, the sort of existence of solutions to Markov chains. It goes on, and they all come for free once you know about LP duality. The way we're going to approach it is to find some useful, a checkable lower bound on my standard form linear program. Actually, you know what? It's 3:15. Before we dive into this topic, let's take a short break and hit it with fresh minds. All right, let's start up again. Okay. So, as I said, what we're going to be trying to do is figure out some way of lower bounding a linear program. Okay? So, let's imagine that we have a standard form linear program, and we want to show a lower bound on it. How can we do that? Well, thinking back to how you sort of tackled linear systems in high school, right? Before you learned matrices and Gaussian elimination and such, what did you do in order to solve a linear system? Well, you would sort of stack up these equations, and you would subtract one equation from another one. You would multiply one of the equations by a constant and subtract it from one of the others in order to cancel out one of the variables and give yourself a linear system with fewer variables, right? Now, we can apply the same sort of idea to linear programs. We can imagine taking linear combinations of inequalities in order to create other inequalities that tell us more about the solution, right? We can imagine that we can multiply each constraint a sub I x equals b by some constant ci, and then we can sum them to get a new constraint. Okay, so we can generate new linear equalities, right? And if you think about what we're doing, right, if we multiply, sorry, by some yi, if we multiply each aix by a yi, we get, yi times aix should be equal to yi times bi. And if we sum those up, right, what we're actually writing is y times ax is equal to y times b, right? We're taking each ax equals b, we're multiplying it by a yi, and then we're adding those up. Okay? So this is just another linear constraint that is also valid for any feasible point. Agreed? Now, if we're clever about this, if we find a y such that ya is equal to c, then we will know that yb, which is equal, thanks to this construction, to yax, is equal to y times, is equal to ya times x. And what is ya? Well, we are forcing it to be c. So this is equal to c times x, right? So if we're able to find a y like this, right, if we're able to combine our linear equality constraints such that ya is equal to c, right, that tells us that cx is equal to yb, and this is true for all feasible x, right? If x is feasible, that means that ax is equal to b, which means that yax is equal to yb, right? Now, what would that mean? If cx is equal to yb for every feasible x, what does that tell us? What is cx in the definition of the original linear program? Right? What role is cx playing here? Yeah?
It's our objective.
Cx is the value of the objective function at x, right? Now, if I tell you that Cx is equal to yb, it has the same value at every x, what is that telling you? Yes?
X is equal to 0 or CX equals 0?
Why? Careful. We can't. These are vectors. We can't sort of cancel things out. We can't divide to cancel things out. Right? All this is telling us is that for every x, Cx has the same value yb. Right? What does that mean? Yeah.
C is 0.
Why?
Because it is a constant.
I did well. Cx is a constant. That doesn't necessarily mean that C is a constant.
Yes, but if C is not a constant, then vary in x, Cx changes.
That's not necessarily true in higher dimension. Right? If I have a set of values x that are all feasible, and C points in this direction, then varying x does not change the value of Cx, right? But what does it tell us, right? All of these x's have the same objective value. So what does that tell me about all of these x's? Yeah?
I mean, they're all optimal.
They're all optimal, right? Every single point in this, every single feasible point has the same objective value. So that means by definition, they're all optimal points, right? So this would imply that all x have the same, and therefore the optimum, objective value. Okay. Now that, of course, is too good to be true or just very unlikely. And that tells us that we're not going to be able to find a y that has this very strong condition. So such a y might not exist. Okay. And in fact, if there is more than one objective value in the polytope, then that y can't exist, right? But instead, right, instead of forcing ya to be equal to c, let's suppose we just managed to get ya to be less than or equal to c. Okay. If ya is less than or equal to c, then by the same argument, as we said before, right, we can take yb, right? And we know that if x is feasible, that yb is equal, that b is equal to ax, so we can write yb as y times ax, right? And now we can move the parentheses and say that this is ya times x, right? Now, what do we know about this? X is feasible, right? I should say that at the beginning. So if we have a feasible x, x is feasible, and what does that mean in standard form? Which x's are feasible? Yeah?
All the coordinates are positive?
All the coordinates are non-negative, right? They also satisfy ax equals b, but we're already using that. But the important thing for our argument is that all of the x's are non-negative. So all of the x's are non-negative. We also know that we have chosen a ya which is less than or equal to c. So if we have a bunch of non-negative values multiplying a bunch of things that are coordinate-wise less than c, right, then we can conclude that the result is less than or equal to cx. Okay? And again, this relies on the x's being non-negative, right? Because it basically prevents you from, right? If you multiply by a negative quantity, you flip the direction of the inequality, right? But since all of the x's are positive, we're taking a bunch of upper bounds, and they stay upper bounds when we multiply, and then we just add them up. And when you add up a bunch of upper bounds, you get another upper bound. Okay? So does everybody agree that this is true? Now, what does it mean for yb to be less than or equal to cx? And again, this is for all feasible x. Well, if we have something that is smaller than all the feasible x's, that means that in particular it's smaller than the optimum, right? So YB is a lower bound. On opt. So this accomplishes our goal of getting a lower bound on opt. Okay? So in order to find a lower bound on the optimum, a proof that you cannot be very good, that your linear program does not have a great solution, all you need to do is find some y that satisfies this collection of inequalities. Okay? And any y that satisfies this collection of inequalities gives you a lower bound, right? The value of the lower bound is y times b. Okay? So to summarize, any y such that ya is less than or equal to c gives a lower bound yb on the optimum value of cx. Okay. Now suppose that you want to get the best possible lower bound. How do you formulate the problem of finding the y that gives you the best possible lower bound? Yes. You need to maximize what? You maximize YB. In other words, to find the best lower bound, what you do is you solve the problem of maximizing YB such that YA is less than or equal to C. What kind of problem is that? Yeah?
Linear program?
That's a linear programming problem, right? So we set out with this goal of finding a lower bound on the optimum of a linear program. And where it took us was to solving a different linear program. Okay. And this is known as the dual LP. To the primal LP, which we started with, minimizing Cx such that Ax equals b and x is greater than or equal to 0. Okay. Everybody with me? All right. So hopefully you see the parallel here to what we were doing with linear systems. Right? What we said was, we want to study this linear program. We're going to gain insight from it by looking at a different linear program. And in a sense, each solution to the dual linear program gives us a bound, gives us a kind of insolvability of the original linear program, right? If I find a y that gives a certain value yb, right, that tells me that I can't find an x that does better than that value yb. Make sense? And this is a duality relationship, right? If I start with this linear program, right, we can run the argument in reverse, right? Because every yb here gives a yb which is less than the cx that you get for every feasible x on this linear program. So every y that's feasible here generates a lower bound on the optimum of this linear program. Every x that's feasible here generates an upper bound on this linear program. So they bound each other. So what we have just shown is what is known as weak duality. namely that the optimum of the dual LP is less than or equal to the optimum of the primal LP. And I mean, the way I've stated it relies on the fact that the primal is a minimization, so it's trying to go down, right? The dual is a maximization, it's trying to go up, and weak duality says that they can't cross each other, those two objective values. Okay. I'll point out something else. You remember I said when I introduced you to linear programming, I said, oh, how nice, we can transform every linear program into standard form. And then I said, but for some reason, people made up another form, the canonical form. Yes? Now you'll notice that if I take this standard form linear program, its dual is a canonical form linear program. So you can't live with just one of them. You sort of get, just by thinking about duality, you get forced to thinking about the other style as well. Okay. However, we can do a little sanity check. Okay. I'm calling this a dual. And thankfully, that name is correct because the dual of the dual is, what do you suppose? Well, it's the primal. Okay. If you go through this process of creating a bounding linear program for the dual linear program, you get back the primal program, slightly in disguise. Okay. Right, our dual was to maximize YB where YA is less than or equal to C. Now, what we've looked at over here is a way of transforming a standard form linear program into its dual. So we need to turn this into a standard form linear program so that we can apply our transformation process, right? So when we do the transformation, what this turns into is computing, we talked about, to switch a max to a min, you negate the objective function, right? And in order to get equality constraints, you introduce these so-called slack variables, right? So when you do this transformation, what you get is minus minimization of minus YB. Actually, yeah, I'll just say YB. And your constraints now are that YA plus your slack variables, and this is the identity matrix because you just have one slack variable for each constraint, should be equal to C, right? The slacks take up the space between YA and C. But all of the slacks have to be non-negative so that YA can never be bigger than C. Okay, so this is the result of our transformation. And if you turn this into matrix form, it looks like, I'm going to transpose things to match my notes, but oh, you also have to get rid of your negative variables. So you actually transform this into minus b times something which involves the positive parts and the negative parts of the, right? This was another part of our transformation where in order to allow variability to be either positive or negative, you had a positive part and a negative part which were both positive and you subtracted. So when you do this, you get a matrix that looks like this. This is your objective function. And your slack variables don't contribute to the objective function. And you are then also restricting to having A and minus A and the identity matrix times the positive y's and the negative y's, and the slacks should be equal to C. Right? So here I have an A and a minus A that represents subtracting off the, using the negation of the negative parts of the variables And again, this is B equals C because we're using the slacks, okay? And now when you take the dual, using the tricks that we provided over here, the LP that you end up with is to take minus maxima of, so if we look at the dualization process, right, we had a B and a C over here, right? B was the right-hand side of the constraints, and C was the coefficients of the objective function. And in the dual linear program, they swapped places, right? The things that were the constraint values turned into the objective in the dual linear program, and the things that were the objective coefficients turned into the right-hand constraints in the dual linear program, right? And so that's what happens here, right? Here, C was our right-hand side constraints, and B was our objective function. When we go through the dual process, they swap back to what they were. C becomes the objective again. Okay. And again, this is literally just plugging it into the transformation that we did before. A minus A and I times, to avoid confusion, I'll use a different variable, Z. That has to be less than or equal to what was the objective function. So again, we had our B became our objective function, but it turns into the right side constraints when we take the dual process. Okay. And if you simplify that out, what you're basically computing is the minimum of minus CZ, such that A times minus Z has to be equal to B, and Z has to be less than or equal to 0. Okay, right? Again, notice here we have A times Z equals minus B, and also minus A times Z is equal to B, but those are both telling you the same thing. So one is redundant, and you just have A times minus Z equals B. And then the last part tells you IZ should be less than or equal to 0. And now you can just set X equal to minus Z, and that gives you back the original linear program. Okay. So, I mean, you can check that math for yourselves if you want. I wanted to get it on the board so that you could look at it, but obviously we're not spending a lot of time on it. You can also just accept that it's true. Yes? What is the negative sign for a minimum? Oh, well, that after you compute the minimum, you negate it.
Okay.
Right? And again, that just follows from just applying the rules that right? When we transform a linear program from standard form to canonical form, or sorry, from canonical form to standard form, we need to change it from a maximization problem into a minimization problem, right? And so how do you turn, right? So in order to turn it from a maximization into a minimization, you negate the objective function. That flips from going from maximum to min, but then you have to negate the result in order to get the same answer as you had before. So you're just doing two negations to cancel each other out, but that replaces the max by the min. Okay? Other questions? All right. So now we can get to some quick and useful corollaries of weak duality. Okay. If P is the primal linear program and D is the dual one, okay, they bound each other. Okay. Right? One provides a bound on the other. So there are only a few possible cases. One is that P, the primal and the dual, are both feasible. And have bounded optima. Right? If the primal and dual are both feasible, it means that there's a point in the primal and a point in the dual. The point in the primal gives you a bound on the optimum of the dual, And the point in the dual gives you a bound on the optimum of the primal. So both of them are bounded if they're both feasible. Okay? Now, another thing that may happen is that P is unbounded. P has an unbounded optimum. Okay? In other words, P, the primal can get as good as you want. Now, if P has an unbounded optimum, what does that tell us about the dual? Yeah? Exactly. Right? That's really just the contrapositive of what we were saying before, right? If P is unbounded, then there's no possible, there can't be a point in the dual because it would provide a bound. Right? You could have the reverse, where D has an unbounded optimum, and P is infeasible. And the last possibility is that both are infeasible. Okay. And a way of sort of capturing all of these, a way of smushing all of these together so that you don't have to talk about cases is if you have a maximization problem, if you have an unbounded maximization problem, you represent that as being a value of infinity. If you're in an unbounded minimization problem, you represent that as having a value of minus infinity. That's pretty obvious. But conversely, if you have an infeasible maximization problem, well, you just say that that means the value is minus infinity. And if you have an infeasible minimization problem, you say that that means that the value is infinity. And under this extended notation, what you're basically saying is that in all cases, the value of the primal, if it's a minimization problem, is greater than or equal to the value of the dual if it's a maximization problem. If the primal is a maximization problem, it goes the other way around. Okay? So that's the story of weak duality, and it gives us a useful way of bounding, bounding the size of a linear program. Okay. All right. So that's nice, but it's not nice enough. Okay. Turns out that we can say more than weak duality. One of the most powerful theorems that we have is what's known as strong duality, which says that if P and D are feasible, then in fact they both have the same optimum. Okay? The bound that you get through the dual is a tight bound. Okay? And I'm going to finish up by giving you a physics proof of this. Okay? So I started out as a physics major before I realized I couldn't do physics. And so this is a hearkening back to the old days when I proved things like a physicist. So it's going to be low on the math, but it has some quite lovely intuition. Before I do that, one logistical point. Monday is the last of the Jewish holidays in this season. I'm going to have to take off again. And so we're going to do one more of those recorded lectures on Monday, which will sort of continue the story of duality. But I can give you this physics story live. And so, yeah, as I said, I'm going to do proof by physics. Actually, I'm going to do proof by picture. Okay. So let me draw the picture, or tell you the physics. So we want to understand a linear program. We're going to solve the linear program physically. So somebody gives us a bunch of constraints. We go to the carpentry shop. We cut a bunch of plywood, and we build the polytope. Okay? We turn the polytope so that the objective function is pointing straight up. Okay? In other words, its height. Okay? And we want to minimize, sorry, I'm going to start with the canonical form. So I'm going to try to minimize by such that ya is greater than or equal to c. Okay? And how I'm going to do that? Well, I'm going to take a ball, and I am going to drop the ball. Okay? So dropping the ball minimizes the objective function, right? Because the objective function is pointing straight up, and the ball is going to fall straight down. Right? So the ball falls, and it lands somewhere in my polytope. Okay? Now the question is, what is the physics that explains what's going on here? Okay? So let's let y star be the minimum height point where the ball ends up. It is the optimum solution to our linear program. The question is, why does the ball stay there? Remember, this is physics class, so why doesn't the ball move? Come on, you all had to take 801, right? Why doesn't the ball move? Yes? Forces, right? The forces are in balance. Okay? Now let's think about what that means for the forces to be in balance. So these are our constraints, right? They are of the form yi times a is greater than or equal to ci. Right? So we've got a collection of these normals. The constraints exert normal forces. YAI, right? Or sorry, they exert normal forces that are in the direction of these normal arrows, right? And what is the what is this normal force, right? This normal is AI, right? And the magnitude of that force is some quantity that I'll call xi. Yes? So mathematically, what does it mean for the normals, for these normal forces to cancel gravity? It means that there are magnitudes, xi, for the different forces, such that the sum of those normal forces cancels gravity. In other words, they cancel gravity. In other words, the sum of ai xi has to be equal to b. In other words, ax has to be equal to b. That's just the definition of the normal forces, right? Canceling out. Now let me point out something else, okay? What can I say about the values of these, what can I say about these magnitudes? Okay? I've pointed all of the normals into the polytope. So what does that tell me about the xi's? Can they be arbitrary numbers? Yeah? Right. Normal forces push, right? These are not magnetic walls that are pulling the ball down. They are pushing the ball away, which means that all of the xi's have to be greater than or equal to 0. Okay? Now, okay, all the xi's have to be greater than or equal to 0, but which of the xi's can be bigger than 0? Which of the planes can actually exert a force on the ball? Yes?
The constraints you're tight against, like the ones the ball is touching.
Exactly. Xi is greater than 0 only if the ball is touching the wall. In other words, the constraint is tight. Okay. So what we've shown now is that our physics experiment gives us an x that is feasible for the dual linear program, right? The dual to the one we started with, right? Now we also know that xi is non-zero only if the constraint is tight. Okay, now another way of writing that, right? Xi is greater than 0 only if yai is equal to bi. Sorry, ci. Right? That's what it means for a constraint to be tight, is that you have equality. Okay? So imagine if I take this vector of x's and dot it with this vector of yai minus ci values. Okay? If xi is positive, then yai is equal to ci, which means that yai minus ci is equal to 0. Right? So if I have a non-zero coefficient in x, the corresponding difference is 0. If I have a 0 coefficient in x, it doesn't matter what's over here. The dot product is still going to contribute 0 in that term. In other words, x dotted with the vector ya minus c is equal to 0. Okay. Now if I unpack that, what that tells me is that yax, sorry, I should put the x on the other side just so that the matrix behaves properly, right? That tells me that yax is equal to cx. Okay. Sorry. Yax equals cx. Right. And what did I say that right, but we just proved above that ax, right, is equal to b. This is the normal forces balance that we proved, right? So what we've actually shown is that yb is equal to cx, just by arguing that the forces are in balance. Okay, and again, we're relying on two things. We're relying on constraints only exerting force if they're tight, right? And this is, we'll come back to this. This is complementary slackness, which we've already seen once in the context of min-cost flow, And because of this, we've concluded that the value yb of the point that our ball landed at is equal to cx, where x is the magnitudes of the forces. Okay? In other words, we have an ax equals b, where x is greater than or equal to 0, and we have a value cx for that linear, for that x, which is equal to a yb, which satisfies ya being less than or equal to c. Okay. So we started with what I called the dual linear program over there. We did some physics, and we got this primal linear program, and we got a solution to each of them, a feasible solution to each of them, where the values of the objectives are equal. Now, we already had weak duality, right? It said that the values can't cross, right? So the equality is the best we can hope for, and we've just shown that it's achieved, just from physics, right? We've shown that you can always get matching values for the primal and dual linear programs. Okay? So this is a case where I quite like the physics, because it sort of just follows very naturally from our intuitions. On Monday, I'll turn this into a mathematical proof. Okay, so so those of you who don't like physics, like me, will trust what I've told you after you see the math. But this is, the math follows exactly what we did here. It just fills in the formal details of it. Okay, so on Monday you'll see that proof, and then I'll start showing you more generally how to take duals and how to use those duals to discover all sorts of interesting things about optimization problems. Except I won't be here, but you'll see it on video. Okay? And then I'll see you on Wednesday.